Great. Hello, I'm Victor Martinez. Most of you know me as VN Martinez in Twitter. And this talk is going to be about fuzzing, but it's not going to be about examples or introduction to fuzzing. It's just going to be about tips that you can use either both auditing and as a developer to improve your fuzzing skills. So a little bit of background. I'm a EVM and security researcher at Turing Consulting and a smart contract auditor at Oak Security. I've been doing bug hunting for a couple of years. As I said, the purpose of the talk is to make, so we need that invariant testing should be the floor of security. So the focus of the talk is to change people's minds and make them really want to implement invariants in their testing suites. I will cover a brief introduction to fuzzing, tooling tips, fuzzing tips, general fuzzing tips. Then I will show some example of both protocols, live protocols, known protocols, and libraries, known libraries too, that use fuzzing in their testing suites, and a few future trends. And if I have enough time left, I will show some bonus alpha. Great. What is fuzzing? I'm pretty sure most of you know what is fuzzing. Fuzzing is a way of testing, but instead of creating your own dataset, your input dataset, you let an automatic program to create all these randomized inputs. You also can leverage that and can make an arbitrary number of calls. So as I said, why do we need fuzzing? I'm saying that humans are dumb, but it's not that one dev is dumber than another. It's just that a human cannot make a million test cases or even come up with a million different inputs. So we let the program do that. We create invariants, we create properties, and we let the program come up with all this, all the brute force. Also, another reason is that devs usually test the happy path, and if they try to test for edge cases, it's not really edge cases, it's just grasping a bit of the weird cases, but not going full depth. Third reason is that coverage is not really a great metric for security. So you can have great coverage, but the test can be bad, very bad. And we need to find a metric or a way to make sure that the test, to improve test quality. And it's also, as I say, it's also super useful to hide these weird edge cases or these weird call sequences. Like, for example, the raft bug 2 days ago, it could be caught. I've seen on Twitter that it could be caught with some invariant testing. Fuzzing techniques. I'm pretty sure most of you have seen either on Twitter or on YouTube tutorials that there's two main techniques. Two branches is stateless fuzzing, when you go from state n to a state n+1, and each time you select a new input, it always goes back to n, and then next n+1. But the good thing is that property-based testing, the other branch, instead of going from state 0 to 1, it goes from state 0 to 1, 2, 3, 4, whatever amount of call depth you put into the tool. So that's where we are able to find these invariants. We're able to find call sequences in all the in all the branches of the tree of possibilities of the state machine that is the smart contract. I'm going to do a brief overview so you can have my opinion on the actual tools of the state-of-the-art of fuzzing. Kidna is still the best tool for the job. Kidna has been around, not really sure the years, but it has to be between 3 and 5. So it's battle tested, it's production ready. It's a bit slow, but it's the only thing we have production ready, and that covers stateful fuzzing. We have Foundry that is very useful to do a stateless fuzzing, but it's not useful for stateful fuzzing. It's very fast because it's written in Rust. And then we have Medusa that eventually will surpass Echidna. It was announced a few months ago, but right now it's on beta. You can use it in your Echidna suite, so you have an Echidna suite and also a Medusa suite, but it's not really recommended to use it alone because, as I said, it's beta, so it's not production ready. Echidna, I'm not going to explain the tool. I'm going to give you a few tips about the tool that can improve your experience. So a great way to trace back on Echidna, so you have an invariant that broke. Instead of tracing back on the Echidna, let's say the printed call stack that on the traces printed, you could take the values and write a unit test of Foundry on top, and then print those and debug like a normal Foundry debug. So it's way easier to test that, to know where the issue is when you have the wrong values. Another great tip is to use already built properties. Like cryptic properties is just a few, it's actually like 40 properties or more for ERCs. And then if you are starting, it's a pretty good recommendation to go to known protocols. I will put a list later. Go to known protocols, testing suites, and follow the best practices they have, follow the harnesses, copy even the config files, and play around with that. There's two testing approaches in Echidna. There's internal testing and external testing. I would recommend just go to external testing because internal testing is just for little contracts that don't require initialization or even just have one entry point. And external testing is what I use 95% of the time. It's contracts that it requires, it needs a lot of overhead. So you have to build either harnesses, config files on top, but it's really useful because you have way more, let's say, you can interact a lot more with the test and do more stuff. Foundry, as I said, is super fast, it's written in Rust. It's perfect for stateless fuzzing. So instead of making a unit test and writing to, for example, if I have one variable that it's amount and hard coding it to 1, instead of that, I will, as you can see on the slides, I will make that variable randomized, and with a config that I put on the TOML file, Foundry will come up with a set of cases and run them in a for loop. The problem with Foundry is that the input generation is always randomized. It's not guided by anything, neither symbolic analysis, symbolic execution, nor coverage guidance, like Echidna. So in order to, when you start putting requirements on invariants, in order to find these little call sequences or these little edge cases, most of the times you are not going to reach them. You would have to run Foundry for months in order to reach them and probably run out of memory. So it's not useful. Just don't bother using invariant testing on Foundry yet. It's my opinion, of course. Then if you are forking, it's better to fork if you have fork tests and you want them to be fast, it's better to fork mainnet with Anvil, and then after that, use the Anvil RPC in your fork suite to not call the live RPC every time you are making each one of these inputs of the tool. And then, as I said, for invariant testing, use either Echidna or a formal verification prover like Certoras. Last tool, Medusa. It's a next-gen fuzzer. It's written in Go, so it's much faster than Echidna, but it has a similar CLA and UX to Foundry. So the look and feel is pretty similar, and the user experience is faster, but as I said, it's not production ready. So we cannot really use it alone. But if you come up with bugs, one cool advice is to ask on GitHub raise an issue because the dev team is super active. Now, general fuzzing tips. I'm really a hater of people oversimplifying things. So every time I see tests with lots of mocks, lots of hard-coded values, or even invariants out of reach, I don't like the testing suite. So make sure when you are doing your invariants that make sure that those are reached. In Echidna, you can see if the invariants are reached with coverage analysis. Avoid mocks, and as I said, avoid oversimplified values. What are oversimplified values? Hard-coded stablecoin prices, hard-coding, as says here, the rebasing token amounts, things like that. Another useful tip is to always prove my libraries. Auditors normally see a library, not normally, but usually they see a library and they don't really, they think that it's already correct. So they don't really jump into testing it. And it's not easy, but it's really straightforward to test a math library. You just put the spec and the math library and compare them if they are always the same. With fuzzing, if they have always the same value. As I said earlier, use existing setups. You can go to all the projects, just copy their config files, harnesses, test suites in order to save time and learn a lot. You can learn a lot from what other top researchers do in the space. And last but not least, read reports from both fuzzing auditors, fuzzing researchers, or formal verification reports, for example, Certora reports, in order to bump up your invariant creation skills, because that's the most difficult part of invariant testing. Fuzzing in real life, I will go fast here. There's a lot of projects that you can go and copy invariants from them, learn invariants from them. There's a couple libraries that use fuzz suites, Solidity and Soulmate. They are both Solidity snippets, so written in assembly. So both of them use a lot of fuzzing in order to make sure to battle test this assembly code. And future trends, hybrid fuzzing is a layer of symbolic execution on top. So instead of coming up with random values, you come up with symbolic values. There's this library that it's like a plugin for Echidna that adds a layer of symbolic execution on top of Echidna. It's called Optic. Then mutation testing is really important here. I was talking about that coverage is not really a good metric. Mutation coverage is really the metric that we should be testing against. So you make your tests, you make your code, you make your tests, you make sure everything runs fine, then you introduce mutations with both of these tools, either Vertigo or Gambit, and then you make sure with every mutation, at least the test crashes. If the test does not crash, your test should be more constrained. And last but not least, I think the next big thing is formal verification. Both even Certora Approver or Halmos. Halmos is a formal verification tool that we are going to see now. What is Halmos is basically just like Foundry stateless testing, but with formal verification, model checking. So instead of, as I said, instead of providing these values randomly, you provide these values symbolically. These values are analyzed symbolically and then are proved the whole property. The properties are proved with for all possible inputs. So the range of error is much less than with Foundry. It works with Foundry test, so there's no overhead. So it's very straightforward. I use it both for my math libraries and also for equivalence testing, because I do a lot of, in Turing Consulting, we do a lot of assembly optimizations. So we have a function, and we have the same function with assembly code, and we are making sure that both functions are equal, so we are doing equivalence testing. There's a good example that Zach Obron did. It's called Halmos Solidity. So he basically made sure that both specs, the operations in Solidity, the operations of Soulmate and the operations of Solidity are formally equivalent. So for all cases of the spectra of symbolic values, they will return the same output. Final takes, because I still have like 1 minute left. So Foundry fuzzing, stateless fuzzing is useful, but it's not that useful. You will catch things, but you will not catch as many things as with Echidna, with invariant testing. Then always use a combination of Echidna. If you are going deep enough, if you are going to build a great fuzzing suite, always use Echidna with other tools. Kidna Foundry, Kidna Medusa, or both, or the three of them, you can solve CTFs, especially math CTFs, with formal verification tools like Halmos. It will come up, it will solve the equation and come up with a solution. And mutation testing is, in my opinion, really the next good metric to measure test quality. And formal verification, last is formal verification is the next big thing, and I hope it goes well in the future. And a lot more open source tools come up to the research community. And that's all. I hope you liked the talk about fuzzing. That's my Twitter. You can ping me if you have any questions.